Welcome to the deep dive. We're going on a mathematical journey today, exploring a novel method for computing signature kernels of long-time series.
Sounds exciting.
It is. We're diving deep into this paper, Scalable Signature Kernel Computations for Long-Time Series via local Neumann series expansions.
Ah, yes, this paper. It introduces an algorithm, PowerSig, that could change how we handle these massive time series datasets.
Right. So for our listeners who might not be familiar with this kind of data, can you explain what time series data is and why it's such a big deal?
Sure, think of anything that changes over time. Stock prices, weather patterns, or even your heart rate. All of these can be represented as time series data, basically a sequence of data points indexed in time order.
Okay, I see. So by analyzing these sequences, we can, uncover patterns and trends.
Exactly. And those patterns help us understand the past, predict the future, and make better decisions. Time series analysis is used in tons of fields: finance, healthcare, you name it.
It sounds like time series data is everywhere. This paper, though, specifically talks about the challenges of analyzing really long time series. What makes them so difficult?
Well, the traditional methods for analyzing time series data, they often struggle when you have these super long sequences. As the data points increase, the calculations get way more complex, and the memory needed to store all that data grows a lot.
So it's like trying to work with a huge puzzle on a tiny table. You just run out of space.
Exactly. That's the kind of bottleneck we run into.
So that's where this signature kernel idea comes in. It sounds like it provides a more efficient way to represent and analyze these complex time series. How does it work?
It's like summarizing a story, right? You don't just list the events, you try to get the overall flow, the relationships between those events. That's what the signature kernel aims to do.
Okay, so instead of looking at each individual data point, it tries to capture the big picture, the essence of the time series.
Exactly. It maps the time series into this mathematical space where we can calculate a measure of similarity between two time series. We call that measure an inner product. This allows us to understand the overall dynamics of the data, even with all the noise and long sequences.
Sounds like a powerful tool.
Yeah?
But the paper mentions limitations with traditional ways of computing the signature kernel. Can you explain those?
Yeah, so the usual approaches, they rely on either dynamic programming or they try to solve this complex mathematical equation called the Gorsat PDE,
PDE.
a partial differential equation. Both these methods, they run into problems with those long time series. They need to store this huge grid of data points, which again leads to those memory constraints.
And that, again, limits how we can apply signature kernels to real-world data sets.
Yeah.
Okay, so how does the PowerSig algorithm solve this?
PowerSig breaks the problem down into smaller, easier to manage pieces. Instead of computing the signature kernel for the entire time series all at once, it divides the time domain into these tiles, and then it approximates the kernel locally within each tile.
Okay, so it's like solving a bunch of mini puzzles instead of one giant one.
Yes, exactly. And they use this technique called the Neumann series expansion, which helps to approximate a function by a series of simpler functions.
So PowerSig applies this to approximate the signature kernel within each tile.
Precisely.
But these tiles, they can't just be isolated, right? They have to be connected somehow to give us the complete picture.
You're absolutely right. And that's the clever part of PowerSig. It connects these local approximations using a recursive formula, which determines how the solution in one tile depends on its neighboring tiles.
So it's like a chain reaction where each tile solution influences the next.
Yeah, like solving a chain of mini puzzles using the edge pieces of one to guide the next one. It's really quite elegant.
That's a great analogy. Now, before we go further into the algorithm itself, I'd like to understand the role of this Gorsat PDE you mentioned earlier.
Right, so the authors of the paper built their work on some earlier research that showed that the signature kernel can be characterized as the solution to this Gorsat PDE. It's a type of PDE that describes how a function changes over a two-dimensional domain. In this case, it's the time domain of our two-time series, and as we discussed earlier, the signature kernel is a function of two time variables.
Okay, I see. So we have this Gorsat PDE that describes our signature kernel, but it's really hard to solve directly for those long time series, right?
Exactly.
So that's where PowerSig comes in. It uses this tile-based approximation, this Neumann series thing, to find the solution locally within each tile. Is that right?
You got it. Instead of tackling the Gorsat PDE head-on, they use it as the starting point for this tile-based approximation. They reformulate the PDE into an integral equation, which then allows them to apply Neumann series recursively, going tile by tile.
Okay, so the paper goes into a lot of mathematical detail about this recursive approach. It's pretty dense, I have to admit. But the main idea, if I'm understanding this right, is that we can calculate this signature kernel within a tile using information from the boundaries of the adjacent tiles.
That's a great summary. Let's break it down a bit further. So they introduced this crucial formula called Proposition 3.5 that provides the instructions for how to calculate the signature kernel within each tile. And this formula really leans on the idea of an integral operator, which they denote by T. It basically describes what happens when we integrate our function over a specific region.
So if I'm getting this right, applying this integral operator repeatedly, like raising it to increasing powers, lets us build the Neumann series approximation within each tile. It's adding more detail to the solution, right?
Precisely. And each term in that series only needs information from the boundaries of the adjacent tiles. So instead of working with this huge grid of data points, we only need a smaller set of boundary values.
That's clever. It saves a lot of memory. So PowerSig manages to calculate the signature kernel both accurately and efficiently by using boundary data and this recursive formula.
Right. But there's another important part. There's lemma 3.3. That guarantees our Neumann series actually converges. It means our approximation keeps getting closer to the true solution as we add more terms. Without this guarantee, the whole thing might not work.
Right, it could just keep going further away.
Yeah.
So lemma 3.3 is like a safety net, making sure our approximation stays on track. And the paper doesn't just give us abstract equations, it provides a concrete example.
Yeah. Example 3.6 walks us through the calculations for 3 specific tiles: sub 1001 sub 2 sub, and sub 2001 sub. It shows how we can start with the simplest tile, sub 11 sub, which is solved directly.
Okay.
And then we use that solution to get the signature kernel in the neighboring tiles, sub 1001 sub and sub 2001 sub. It really helps to visualize how all the pieces fit together.
It's like seeing the gears turning in the mathematical engine. Besides this formula, are there any other tricks PowerSig uses to get that computational efficiency?
Well, one big advantage is that the calculations in each tile can be done independently, in parallel. We can break down the problem into these separate pieces that can be processed simultaneously by multiple processors or even a GPU.
So we're not just doing less computation, but we're also computing smarter.
Right. And to be even more efficient, PowerSig also uses a dynamic truncation strategy. So it figures out how many terms to keep in the Neumann series for each tile. Sometimes you only need a few for a good approximation, sometimes you need more. PowerSig adjusts this on the fly to get a good balance between accuracy and how much computation is needed.
It sounds like it's custom fitting the solution for each tile.
Yeah.
Okay, so we have this elegant mathematical framework, this recursive formula, and this dynamic truncation strategy. It all points to significant advantages over traditional methods. But does it work in the real world? Did the authors test this theory out?
They did. They compared PowerSig against ksig.
Ksig.
Yeah, it's a state-of-the-art library that uses both dynamic programming and those PDE-based approaches. They focused on computing the self-signature kernel of two-dimensional Brownian motion datasets, so essentially simulating random movements over time.
Brownian motion, that's like the random movement of particles, right?
Sure.
Like in a fluid.
Exactly. It's a common model for random processes, and the results are pretty impressive. PowerSig is more accurate, especially for short to medium-length time series, even when using only a few terms in that Neumann series.
So even with a simplified approximation, PowerSig is outperforming the more complex methods in many cases.
Yeah, it really shows how efficient those local approximations can be. But the most impressive part is the memory usage. It's drastically lower. PowerSig can handle time series with hundreds of thousands of points while using way less memory than the other methods.
That's a game changer, being able to handle those massive data sets.
It is.
Before we get too carried away with all of this, did the paper mention any limitations or things they could improve?
They did mention that while PowerSig has the same worst-case time complexity as the existing methods, in practice, it benefits a lot from that tile-wise structure. They also pointed out a few areas where they could refine the method, like optimizing the computation of those boundary values we talked about.
So there's always room for improvement. But even as it is, PowerSig is a big step forward in how we can analyze and understand these complex time series, especially since they're becoming so common.
I agree. This paper shows how powerful it can be when you combine deep mathematical understanding with clever algorithm design.
Well said. I think we've covered a lot today. We've explored signature kernels, Neumann series expansions, and this PowerSig algorithm. But I feel like we're just getting started.
You're right. The real potential of PowerSig is going to come out as researchers explore its uses in different areas. Imagine the possibilities.
Exactly. And speaking of applications, in part 2 of this deep dive, we'll explore some of those real-world applications and dig deeper into the math behind PowerSig. We'll take a closer look at that proposition 3.5 and break down that recursive formula that makes this method so powerful. Welcome back to the deep dive. In the last part, we got introduced to signature kernels, and we talked about how PowerSig can help with the challenges of analyzing those really long time series.
Right.
Now let's dig a bit deeper into the math behind PowerSig.
Okay, sounds good. We'll unpack that formula from proposition 3.5 in the paper. It's at the core of how PowerSig works.
I'm ready for some more math. Proposition 3.5 gives us the formula for calculating the signature kernel within each tile. It's denoted by G. It's a bit much, but I think I'm starting to get it.
It takes some time to understand. Let's break it down. The left-hand side of the equation, that's the signature kernel key, but it's limited to a specific tile. We call that tile tsubi sub.
Right, so D Pookie are like the coordinates of the tile.
Exactly. So tsubi sub gives us the value of the signature kernel for just that part of the time series covered by the tile.
Got it. So what's on the right-hand side?
That's where the Neumann series expansion comes in. It tells us we can express tsubi sub as a sum of terms. And each of those terms involves applying an integral operator over and over. They use tsubi sub to represent that operator.
Ah, tsubi sub. That's the thing that integrates our function over the tsubi sub, right? And we keep applying it, raising it to higher powers each time we get a new term in the Neumann series.
Exactly. And here's the key. Each of those terms, tsubi, sub raised to some power and applied to a function, we can calculate that using information only from the boundaries of adjacent tiles.
That's where the efficiency comes from. We're only dealing with boundary values.
Right. And the function that tsubi sub is applied to, it's a combination of q values evaluated at specific points on the boundary of our tile. Those points are represented by tsubi sub and tsubi sub.
So those are like the coordinates of the corner of our tile.
Yes, bottom left corner.
Okay, so we're using these known values of key on the boundaries to get the value inside the current tile.
Exactly. The formula also includes the initial conditions. Those are the values of at the very edges, where one of the time coordinates is 0. They use key sub, sub sub, and kupi sub for those.
Right, those are like our starting points, and we build up from there tile by tile.
Precisely. And to make it all clearer, they have example 3.6, which shows how to do this for tiles sub 100,001 sub, sub 1,000 sub, and sub 2,001 sub.
Yeah, that example really helped me understand it. It starts with sub 11 sub, the one in the corner. We can solve that one directly using Bessel functions.
Right, those are special functions we see in physics and engineering.
And once we have sub 1001 sub born, we can use that to get the neighboring tiles. Sub 1000 born uses the values from the boundary it shares with sub 1001 sub.
And the initial condition along the bottom edge.
Right.
Yeah,
and sub 21 sub uses the values from sub 1 sub sub and the initial condition along the left edge. It's like watching the solution spread across the grid.
Exactly. That's just a small part of the whole process, though. We keep doing this for all the tiles until we get the signature kernel for the entire time domain.
It's pretty amazing. They've taken this really complex problem and broken it down into these manageable steps. Now, we've talked about the memory savings.
Yes.
PowerSig uses less memory because we're only working with boundary values. But how do we choose the size of those tiles? Is there a best size?
That's a good question. The paper doesn't say there's an optimal size. It just emphasizes that PowerSig's structure gives us flexibility. We can adapt to the data.
So maybe we could adjust the tile size depending on what the time series looks like in a specific region.
That's right. If a region has lots of variation or changes quickly, we might want smaller tiles to capture all those details.
And if it's smoother, we could use larger tiles without losing too much accuracy.
Exactly. It's like using different brush sizes depending on what you're painting.
I like that analogy. So PowerSig can adjust to different levels of complexity in the time series.
Yeah. And then there's the parallel processing. We talked about how calculations in each tile can be done independently.
Right, at the same time.
So we can use multiple processors or a GPU to speed things up. This is really important when you have millions or billions of data points.
That's a lot of tiles.
It is. But with parallel processing, we can share the work and get it done much faster.
It's like having a team of mathematicians all working on different parts of the problem.
Exactly. And don't forget about the dynamic truncation. It plays a key role in making PowerSig even more efficient.
Right, by adjusting how many terms we keep in the Neumann series.
We only use what we need for each tile, so we don't waste time.
It's really clever. Okay, so the paper mainly focuses on how PowerSig works and how efficient it is. But it also hints at the bigger picture. It suggests that PowerSig could let us analyze even more complex time series data that we couldn't handle before.
It does. They mention potential applications in areas like finance, medical diagnostics, signal processing.
All sorts of areas. Let's talk about some of those applications in more detail.
Okay.
For example, how could PowerSig be used in finance?
Well, think about financial data, like stock prices.
Okay.
It's very noisy, very complex. Traditional methods have a hard time finding patterns, but PowerSig can handle these long, high-dimensional time series, which could be a big advantage in finance.
So it could help analysts to find those hidden patterns leading to better predictions.
Exactly. Hedge funds could use it to find trading opportunities. Risk managers could use it to assess risk more accurately. And with so much high-frequency trading data available now, the need to analyze these long time series is only growing.
It sounds like PowerSig could change how people invest. What about healthcare? We talked about diagnostics before.
Right. So in healthcare, we have data from ECGs, EEGs, glucose monitors, all sorts of things. These time series tell us about a patient's health, but it can be hard to extract the information, especially when you have long recordings.
And we have even more of this data now with wearable sensors.
Exactly. PowerSig can handle those long time series and capture the big picture. It can help us create better diagnostic tools.
Tools that can detect diseases earlier, personalize treatment, and monitor patient recovery better.
Precisely. It's like having a powerful tool that can zoom in on those subtle details in our physiological signals and tell us what's going on.
This all sounds amazing, but before we get too excited, I want to go back to the math for a minute. In part 1, you mentioned Bessel functions. Can you explain how those are used in calculating the signature kernel, especially for that initial tile, sub 1, 1 sub?
Of course. The signature kernel, remember, it captures the essence of a path's geometry. With sub 1 sub, since it's in the corner, we're looking at paths that start at the origin. And the signature kernel, in this case, it's connected to the expected value of certain functionals of those paths.
And that's where Bessel functions come in.
Exactly. They use a specific type, the modified Bessel function of the first kind. It lets them compute the signature kernel for sub 1 sub directly without needing any information from other tiles.
Okay, so it's a shortcut for that first tile.
Mm-hmm.
But what about the integral operator, subi sub? How is that used in the formula?
So the subi sub operates on functions defined on the tiled subi sub. It takes a function, integrates it against a specific kernel, and then evaluates the result at a point in the tile. The kernel function is derived from the solution to that Gorsat PDE we talked about.
Right, the Gorsat PDE. So the kernel function basically links the signature kernel and the PDE.
Exactly. The recursive formula uses this integral operator to spread the solution from one tile to its neighbors. We apply subi repeatedly to build up the Neumann series, which gets us closer to the true signature kernel within each tile.
It's like a chain reaction of information.
It is.
Now, we've talked about Lemma 3.3 and how it guarantees the convergence of the Neumann series. Could you explain how they proved that lemma? Why is it so important for PowerSig to work?
Sure. Lemma 3.3 basically says that under certain conditions, the Neumann series we use to approximate the signature kernel, it will actually converge. It'll get to a real answer.
Okay.
The proof uses properties of that integral operator, subi sub, and something called the operator norm. That measures the size of the operator, mathematically speaking.
Not the physical size.
Right. It's more like a measure of its strength or influence.
I see.
They show that the operator norm subi sub is less than 1 under the right conditions. That means that when we keep applying subi sub like we do in the Neumann series, the terms we get, they keep getting smaller.
Like they're fading away.
Exactly. And that's super important because it means the whole series converges to a finite value. Without that, PowerSig wouldn't work. We couldn't trust the answers it gives us.
Right. It would be like building a bridge on shaky ground.
Exactly. Lemma 3.3 makes sure the math is solid. It's the foundation that PowerSig is built on.
Okay, that makes sense. Now, we've mainly talked about the self-signature kernel, which compares a time series to itself. But signature kernels can also compare different time series, right?
Right. We'd be looking at the cross-signature kernel then. It measures the similarity between two different paths.
Would PowerSig need to change to compute that?
The main ideas still apply. We'd still divide the time domain into tiles and use that recursive formula, but there would be some adjustments, especially with the boundary conditions.
Oh, right, because now we have two different paths to consider.
Exactly. For the self-signature kernel, we had those initial conditions along the edges where one time coordinate is 0. Those come from the Bessel function solution for sub 1001 sub.
They're like the starting points.
Yeah, right. But with the cross-signature kernel, we have two paths, so we need boundary conditions along two edges, reflecting the initial segments of both paths.
So we'd have initial conditions on more edges of the grid.
Exactly. We'd need to change the formula to include those, but the basic idea of using the integral operator to move the solution from tile to tile, that stays the same.
So PowerSig is flexible enough to handle both types of kernels.
Yes, with some tweaks.
Now, I want to talk more about the parallel processing. We said the calculations in each tile can be done independently. But how would that actually work? How do we spread the work across multiple processors or a GPU?
So the key is that once we have the boundary values for a tile, we can calculate the signature kernel for that tile without needing anything from other tiles. So we can give each processing unit a tile to work on, and they can all work at the same time.
It's like a team effort.
It is. And to do this, we can use different approaches. There's multi-threading on a CPU or using a GPU, which is really good at parallel processing.
What's special about GPUs?
GPUs are designed for these massive parallel computations. They have thousands of cores that can work at the same time.
Ah, so they can handle lots of calculations simultaneously.
Exactly. They're great for things like matrix operations, which are common in PowerSig, and other areas like deep learning.
Right, because the integral operator involves integration over 2 dimensions.
Precisely. The GPU can do those calculations super fast, which makes PowerSig much more efficient.
Okay, so it's a combination of clever algorithms and powerful hardware.
Exactly.
We've talked a lot about the technical side of PowerSig. But let's talk about how it could be used in the real world. You mentioned finance and healthcare. How could PowerSig address real challenges in those areas?
Let's start with finance. Financial time series data like stock prices, it's complex, it's noisy. Traditional methods struggle with that.
Yeah.
But PowerSig can analyze these long, complicated time series efficiently.
So it could be used to find new trading strategies, uncover hidden trends in the market, or even just assess risk better.
Right. Hedge funds could use it to analyze tons of data, find those profitable trades. Risk managers could model complex financial instruments. And with all the high-frequency trading data we have now, PowerSig could be a game changer.
It sounds like it. What about healthcare? We talked a bit about diagnostics earlier.
In healthcare, we have time series data from things like ECGs, EEGs, glucose monitoring. All of this data tells us about a patient's health, but it can be tough to find the important information, especially in long recordings.
And we have even more data now with all the wearable sensors.
Exactly. PowerSig can handle those long time series, and it can find the bigger picture. It could help create better diagnostic tools.
Tools that can detect diseases earlier, personalized treatments, that kind of thing.
Yes, it's like having a super powerful tool that can see those tiny details in our physiological signals, the details that might point to a health problem.
It's amazing how much potential this has.
It is.
Now, before we move on, I want to go back to the math for a minute. We talked about Bessel functions and the integral operator. I'd like to dig a bit deeper into that. For example, what kind of Bessel function is used in the calculation for sub between sub-sub?
So they use the modified Bessel function of the first kind. It's often denoted as ISU b sub x. It comes up when they're calculating the expected value of certain things related to Brownian motion paths that start at the origin. The reason they use this particular Bessel function is because there's a connection between Brownian motion and something called the heat equation. The solution to the heat equation is linked to these expected values.
It sounds complicated, but also really beautiful. There are all these connections.
There are. They use this to find a direct solution for the signature kernel in sub below 1 sub using that Bessel function.
Okay, so it's a special case. What about the integral operator, subi sub? Can you remind us how that's defined and how it's used in the formula?
Of course. The integral operator subi sub x on functions that are defined on the tiled subi sub. So basically, it takes a function, integrates it against a specific kernel function, and then evaluates the result at a point in that tile. And that kernel function comes from the Gorsat PDE.
Right, so it's connecting the signature kernel and the PDE again.
Exactly. It's basically saying, hey, here's how the solution at one point in the tile depends on the values at other points.
Hmm.
The form of this kernel function can be really complex, but it comes directly from analyzing the Gorsat PDE.
It's incredible how they've taken this complex PDE and turned it into this recursive algorithm that we can actually use.
It is. It shows how powerful math can be when you combine it with smart algorithms.
Now, we've talked about the integral operator and how it spreads the solution. But what about lemma 3.3? That lemma that guarantees the convergence of the Neumann series. Could you walk us through how they proves that? Why is it so critical for the PowerSig algorithm?
Sure. So lemma 3.3 essentially says that if we have the right conditions, the Neumann series, that infinite sum we use, it will actually converge to a real finite value.
We won't just keep going forever.
Right. And the proof uses properties of the integral operator, b sub, and this idea called the operator norm. It's a way to measure the size of an operator mathematically.
Okay.
And they show that under the right conditions, the operator norm of b sub is less than 1. This is really important because it means that as we apply b sub over and over again, the terms in the Neumann series get smaller and smaller.
So they eventually become negligible.
Exactly. And that shrinking of the terms is what guarantees that the whole series converges to an answer. Without it, PowerSig wouldn't be reliable.
Right. The approximations wouldn't mean anything. So lemma 3.3 is like a safety check, making sure the math is sound.
Exactly.
Okay, so far we've mainly talked about the self-signature kernel, the one that compares a time series to itself. But the signature kernel can also be used to compare different time series, right?
Yes, that's right. We call that the cross-signature kernel. It gives you a measure of similarity between two different paths.
Okay. Would we need to change PowerSig to compute the cross-signature kernel?
The core ideas of PowerSig are still applicable. We would still break down the problem into tiles and use that recursive formula to approximate the kernel in each tile. But there are some adjustments we'd need to make, particularly with the boundary conditions.
Oh, right, because now we're dealing with two separate time series.
Exactly. When we calculate the self-signature kernel, we have those initial conditions along the edges of the domain where one of the time coordinates is 0.
Right.
And those initial conditions, they're determined by the Bessel function solution we have for the first tile, sub 1000 sub. But when we're working with the cross-signature kernel, we have two distinct paths, which means we have to think about boundary conditions along two edges of the domain.
So we need to account for the initial segments of both paths.
Precisely. We would need to incorporate these additional boundary conditions into the recursive formula, but the underlying idea of using the integral operator to propagate the solution from tile to tile, that remains the same.
Okay, so the framework is flexible enough to handle both types of kernels.
It is. The main idea of dividing the problem into those smaller tiles and using the recursive formula with the Neumann series, that's central to both the self-signature and cross-signature kernels.
Great. Now, I want to circle back to the parallel processing aspect. We mentioned earlier that the computations for each tile can be done independently. Can we get into the specifics of how that parallelization would actually work? How would we distribute those computations across multiple processors or a GPU?
Sure. The beauty of PowerSig is that once you have the boundary values for a given tile, you can compute the signature kernel within that tile without needing any information from other tiles.
Okay.
That means we can give each processing unit its own tile to work on. They can all compute in parallel.
It's like a team of mathematicians, each tackling their own part of the problem.
Exactly. In a practical sense, we can accomplish this using various techniques. We can use multi-threading on a CPU, or even better, we can harness the power of a GPU, which is specifically designed for large-scale parallel processing.
Can you talk a bit more about how a GPU would be used in this context?
Absolutely. GPUs are incredibly powerful for handling these large-scale parallel computations. They have thousands of cores that can work simultaneously, which makes them perfect for tasks like matrix operations, and those are heavily used in PowerSig.
Right, because the integral operator involves those integrations over 2 dimensions.
Exactly. Those integrals can be approximated numerically using methods like quadrature, which essentially boils down to matrix operations, and GPUs are incredibly efficient at performing these matrix operations.
So the GPU speed is a key factor in making PowerSig efficient.
Absolutely. By distributing the computation for each tile across all of the GPU's cores, we can significantly accelerate the overall computation.
So we're leveraging both the cleverness of the algorithm and the raw power of modern hardware.
Precisely. And that combination is really pushing the boundaries of what's possible in many areas of science and engineering.
Now, shifting gears a bit, we've delved into the technical details of PowerSig, but I'd love to talk about its real-world impact. Earlier, you mentioned potential applications in finance and healthcare. Can we explore those in a little more detail? How might PowerSig be used to solve real problems in these domains?
Sure. Let's start with finance. Financial time series data like stock prices or currency exchange rates are incredibly complex. They're noisy, there are hidden patterns, and traditional methods often struggle to analyze them effectively.
Yeah.
PowerSig, with its ability to handle these long, complicated time series efficiently, could be a real game changer in the financial world.
I can see how it could lead to more sophisticated trading strategies or help us identify market trends that are otherwise hidden.
Exactly. Hedge funds, for instance, could leverage PowerSig to analyze massive amounts of market data and pinpoint profitable trading opportunities. Risk managers could use it to model complex financial instruments and assess risk more accurately. And as high-frequency trading becomes even more prevalent, the need to analyze these long time series will only grow.
It sounds like PowerSig could change how we think about investing and managing risk.
Hmm.
Now, what about healthcare? We touched on diagnostics earlier. Could you expand on how PowerSig might be used in that area?
Absolutely. Healthcare is full of time series, data ECGs, EEGs, continuous glucose monitoring, and more. These time series provide valuable insights into a patient's health, but it can be difficult to extract those insights, especially from lengthy recordings or when dealing with subtle anomalies.
And with the increasing popularity of wearable health sensors, we're generating more and more of this data all the time.
Exactly. PowerSig, with its capability to handle those long time series and capture global characteristics, could revolutionize medical diagnostics. It could help us develop more sensitive and accurate diagnostic tools, tools that can detect those early warning signs of disease, personalize treatment plans, and monitor patient recovery more effectively.
It's like having this incredible tool that can zoom in on those subtle details in our physiological signals and reveal hidden patterns that might indicate a health problem.
That's a great way to put it. And beyond diagnostics, PowerSig might also prove valuable in areas like drug discovery and personalized medicine.
Oh, wow. How so?
By analyzing massive genomic data sets and patient health records, it could potentially help us identify new drug targets or predict how individuals might respond to different treatments.
That's incredible. The potential applications are really exciting.
They are. This research opens up so many promising avenues for exploring and understanding the intricate systems that impact our health and well-being.
Now, as we wrap up this part of our deep dive into the world of PowerSig, I think it's important to address a critical aspect that we haven't discussed yet: the ethical implications of this technology.
You're absolutely right. That's an essential point. Like any powerful tool, PowerSig has to be developed and used responsibly, with careful consideration of its potential impact on individuals and society.
For instance, in finance, the ability to analyze massive time series data sets and potentially predict market movements with more accuracy than ever before that could give certain individuals or institutions a significant advantage.
You're right. It could potentially lead to market manipulation or worsen existing inequalities.
Exactly.
We have to think about the potential for misuse and put safeguards in place. We need regulations and ethical guidelines to make sure that technologies like PowerSig are used responsibly for the benefit of everyone.
And in healthcare, the use of PowerSig to analyze patient data raises important questions about privacy, data security, and algorithmic bias.
Absolutely. We need to make sure that sensitive medical information is protected, that the algorithms we use are fair and unbiased, and that patients have control over how their data is used.
These are complex issues, and they require careful thought and collaboration. We need researchers, policymakers, ethicists, and the public all working together.
I completely agree. As we continue to advance in artificial intelligence and data science, we have to prioritize ethical considerations and make sure that these technologies are used to improve lives and promote a more just and equitable world.
Well said. In the next part of this deep dive, we'll continue exploring PowerSig's capabilities and delve into some of the practical aspects of using it. Welcome back to the deep dive. We've spent the last two parts exploring signature kernels and the PowerSig algorithm, covering the theory, the math, and even some potential uses.
It's been quite a journey.
It has. Now, I want to get practical. How accessible is this technology? What do we need to think about if we want to use PowerSig in the real world?
Well, the great news is that the authors made their PowerSig implementation open source. It's a library built on PyTorch, and it's optimized for GPUs.
That's fantastic. So even if you're not a mathematician, you can still try out PowerSig.
Absolutely. That's the beauty of open source. It makes cutting-edge research accessible to a wider audience. It encourages collaboration and innovation.
So we can all contribute, even if we're not math experts.
Exactly. And the GPU acceleration is important too. It means you can use the power of modern graphics cards to speed up those computations, even for massive data sets.
That's key, especially as data sets keep getting bigger and bigger. Now, even though PowerSig is a big step forward, I'm sure there are still areas for improvement.
Of course. The paper mentions a few things they could work on. For example, optimizing the calculation of those boundary values.
Right, and they also mentioned developing more rigorous error bounds for the Neumann series approximations.
Exactly. Making the boundary value calculations more efficient could make PowerSig even faster and more scalable. And tighter error bounds would give us a better understanding of how accurate the approximations are.
It's all about refining and improving.
It is. And there's also the exciting prospect of seeing how PowerSig works with different types of time series data in different fields.
Testing it out in new areas.
Yeah. The paper used Brownian motion datasets as a benchmark, but it would be interesting to see how PowerSig handles time series with different characteristics, like long-range dependencies or seasonality.
Time series that are more unpredictable.
Exactly. Seeing how it performs in those scenarios would really show its robustness. And exploring its use in fields like climate modeling or genomics, that could lead to new discoveries.
The possibilities are really vast. It's like giving a chef a whole new set of ingredients and techniques. Who knows what they'll create?
I like that analogy.
Now, in part 2, we started digging into the math. You mentioned Bessel functions and the integral operator. Could we go even deeper into that? What kind of Bessel function is used for that initial tile sub1 sub?
Sure. They use the modified Bessel function of the first kind, often written as subi sub x. It comes up when you're calculating the expected value of certain quantities related to Brownian motion paths starting at the origin. They use this particular Bessel function because of the connection between Brownian motion and the heat equation. The solution to the heat equation is related to the expected value of these Brownian motion paths.
Wow, it's all connected.
It is, and this connection lets them find that direct solution for sub 1 sub using that Bessel function.
Okay, so it's like a shortcut. What about the integral operator, subi sub sub? Can you remind us how it's defined and how it fits into that recursive formula?
So the integral operator, subi sub, it operates on functions on the tiled subi sub. It takes a function, integrates it against a special kernel function, and then evaluates the result at a point in the tile. And that kernel function comes from the solution to the Gorsat PDE.
Right, the Gorsat PDE is like the foundation for all of this.
Exactly. The kernel function basically tells us how the solution at one point depends on the values at other points. Its form can be quite complex, but it's derived from the Gorsat PDE.
It's amazing how they managed to take this complex PDE and make it into something we can actually compute.
It is. It's a beautiful example of combining deep mathematical understanding with smart algorithm design.
Now, we also talked about lemma 3.3, that lemma that says the Neumann series actually converges. Can you walk us through how they prove that and why it's so important?
Absolutely. Lemma 3.3 says that if certain conditions are met, that Neumann series we use, that infinite sum, it will actually converge to a finite value.
It won't just go on forever.
Right. And the proof relies on properties of that integral operator, subi, sub, and something called the operator norm, which is a way to measure the size of the operator.
Okay.
What they show is that under the right conditions, the operator norm of subi, sub, is less than 1. That's crucial because it means that when we apply subi sub repeatedly, like we do in the Neumann series, those terms get smaller and smaller.
So eventually they become insignificant.
Exactly. And that shrinking of the terms is what guarantees that the whole series converges to a real answer. Without that guarantee, PowerSig wouldn't be reliable.
It'd be like building on a shaky foundation.
Precisely. Lemma 3.3 ensures that the math is solid.
Now, we've mostly focused on this self-signature kernel, comparing a time series to itself. But we know that signature kernels can also compare different time series, right?
Right. We call that the cross-signature kernel. It measures the similarity between two separate paths.
Would PowerSig need to be changed to calculate the cross-signature kernel?
The core ideas would still apply. We'd still divide the problem into tiles and use the recursive formula, but we would need to adjust things, mainly the boundary conditions.
Right, because now we're dealing with two different paths.
Exactly. With the self-signature kernel, we have those initial conditions along the edges of the domain where one of the time coordinates is 0. Those come from the Bessel function solution we have for that first tile.
Okay.
But for the cross-signature kernel, we have two distinct paths, so we need to consider boundary conditions along two edges, reflecting the initial parts of both paths.
So we'd have initial conditions on more edges of our grid.
Precisely.
Right.
We'd need to modify that recursive formula to account for that, but the idea of using the integral operator to move the solution from tile to tile, that stays the same.
So PowerSig can handle both types of kernels.
It can, with some modification.
Now, I want to talk a bit more about parallel processing. We've said that the calculations for each tile can be done independently, but how would we actually implement that? How would we split up the work across multiple processors or a GPU?
The great thing about PowerSig is that once you have the boundary values for a tile, you can compute the signature kernel within that tile without needing anything from other tiles.
Okay.
So you can give each processing unit its own tile to work on. They can all compute at the same time.
Like a team of mathematicians all working in parallel.
Exactly. We can do this using multi-threading on a CPU, or even better, using a GPU, which is designed for this kind of parallel processing.
What's special about GPUs for this kind of work?
GPUs are built for these massive parallel computations. They have tons of cores that can work simultaneously, making them perfect for matrix operations, which PowerSig uses a lot.
Right, because of the integral operator and those two-dimensional integrations.
Precisely. And GPUs are really good at those matrix operations. So by spreading the work across the GPU's cores, we can speed up the computation significantly.
So it's about using the right tools for the job.
Exactly. Combining a clever algorithm like PowerSig with powerful hardware like a GPU can really push the limits of what we can do.
Now let's step back from the technical details and talk about the real-world impact of PowerSig. We've touched on potential applications in finance and healthcare. Can we explore those in more detail? How might PowerSig be used to tackle real-world problems in those areas?
Sure. Let's start with finance. Financial time series like stock prices and exchange rates are notoriously complex and noisy. Traditional methods often struggle to analyze them effectively.
Yeah.
PowerSig's ability to handle those long, complicated time series efficiently could be a game changer in finance.
It could lead to more sophisticated trading strategies, identify those subtle market trends that are hard to spot, or help assess risk more accurately.
Exactly. Hedge funds could use it to find those profitable trading opportunities. Risk managers could use it to model complex financial instruments and get a better handle on risk. And with high-frequency trading generating so much data, the need for tools like PowerSig is only growing.
It sounds like it could really change how we think about investing and managing risk. What about in healthcare? We talked about diagnostics earlier.
Yeah.
Right. In healthcare, we have time series data from ECGs, EEGs, continuous glucose monitors, all sorts of things. These time series can tell us a lot about a patient's health, but it can be hard to extract that information, especially when you have really long recordings or subtle patterns to detect.
And with wearable sensors becoming more common, we're only going to have more of this data to deal with.
Exactly, and that's where PowerSig comes in. It can handle those long time series and capture the big picture. It could help us develop better diagnostic tools.
Tools that can catch diseases early, personalize treatments, monitor recovery better.
Precisely. It's like having this incredibly powerful tool that can zoom in on tiny details in our physiological signals and reveal hidden patterns that we might not see otherwise.
It's incredible to think about the possibilities. But as with any powerful technology, we have to consider the ethical implications. We haven't talked much about that yet.
You're absolutely right. We have to develop and use PowerSig responsibly. We have to think about the potential impact on individuals and society.
For example, in finance, the ability to analyze massive data sets and potentially predict market moves with greater accuracy could give some people an unfair advantage.
Exactly. It could lead to market manipulation or make existing inequalities even worse. We have to be very careful about that. We need regulations and ethical guidelines to ensure that technologies like PowerSig are used for the benefit of everyone, not just a select few.
And in healthcare, there are concerns about privacy, data security, and algorithmic bias when using tools like PowerSig to analyze patient data.
Absolutely. We need to make sure that sensitive information is protected, that the algorithms we use are fair, and that patients have control over their data.
These are complex issues that require a lot of thought and collaboration.
They do. We need researchers, policymakers, ethicists, and the public to work together to ensure that technologies like PowerSig are used ethically and responsibly.
I completely agree. As we continue to push the boundaries of what's possible with AI and data science, we have to prioritize ethical considerations and work towards a future where these technologies are used to improve lives and create a more just and equitable society.
I couldn't have said it better myself.
Well, I think this has been an incredible deep dive. We've explored the math behind PowerSig, the technical details, the potential applications, and the ethical considerations.
It's been a fascinating journey.
It really has. And to our listeners, we hope this deep dive has sparked your curiosity about data science and its impact on our lives. Even complex algorithms are built on mathematical principles, and anyone can understand them with some effort and curiosity. So keep exploring, keep learning, keep questioning.
The world of data science is full of incredible things waiting to be discovered.
And on that note, we'll wrap up this deep dive. Until next time. All right, so today let's take a deep dive into something really cool. It's called PowerSig.
Okay.
And PowerSig is this new method that's making some waves in the world of time series analysis.
Interesting.
Yeah, and signature kernels are already like super useful for things like finance and machine learning, but they've always kind of hit this like wall, when you're dealing with these really long sequences of data, just because of memory limitations.
Yeah, I see.
It's like they just can't handle it.
Yeah, makes sense.
And well, PowerSig seems to have like cracked the code a bit
Oh, wow.
with some seriously clever math tricks.
Like what?
Well, they're using these things called local power series expansions.
Okay.
And then there's this whole dynamic truncation thing.
Interesting.
And get this, they even made it open source
Oh, very.
and PyTorch based so anyone can jump in and use it.
That's awesome.
What really blows my mind is how they managed to pull it off.
Yeah.
Especially when it comes to those memory constraints.
Right.
It's like, how did they squeeze all that computing power into something that doesn't just explode your computer?
It is pretty remarkable the way PowerSig deals with this challenge. It's by being super clever and taking advantage of local computations.
Right.
So instead of, trying to compute the entire signature kernel at once, which, let's be honest,
Oh, yeah.
can be a memory hog, especially for long time series.
Absolutely.
It breaks the problem down into smaller bite-sized pieces.
Okay, that makes sense on like an intuitive level.
Yeah.
But how does that work mathematically? I mean, we don't want to like sacrifice the accuracy of the signature kernel just to make it easier on our computers, right?
Oh, absolutely. And that's where the real genius of their approach comes in.
Okay.
They've figured out a way to keep that accuracy of the signature kernel, but at the same time shrink down that memory footprint.
Wow.
And one of the key innovations here
Yeah.
is using these things called local Neumann series expansions.
Local Neumann series expansions.
Yeah, so basically they're dividing the time series into these smaller chunks. They call them tiles.
Tiles.
And then they use these really cool math tricks, these Neumann series, to approximate the signature kernel on each of those little tiles.
So instead of tackling the whole time series all at once, they're kind of zooming in on these smaller segments and figuring things out piece by piece.
Exactly. That's a great way to put it.
That's really interesting. But how do they make sure that all these little approximations actually add up to an accurate representation of the whole signature kernel?
That's where the dynamic truncation comes in.
Dynamic truncation.
It's their secret sauce, really. They've developed this method that decides how many terms to keep in each local expansion. It's all about finding the right balance.
Balance between
Getting enough information to maintain accuracy,
right.
but without making the computation go crazy.
So it's not just about breaking the problem down, but also about being super precise with how they put it all back together.
You gotta, it's like a tailor making a custom fit suit.
Ooh, I like that.
Just the right amount of material for a perfect fit.
No wasted fabric.
Exactly.
This is starting to sound pretty ingenious, but before we get lost in the specifics,
Yeah.
I think it's worth taking a step back for a second and just reminding ourselves why signature kernels are so powerful in the first place.
Good point.
Like what makes them so special compared to other ways of analyzing time series.
You're right. It's easy to get caught up in all the technical details and lose sight of the bigger picture.
Absolutely.
What makes signature kernels so amazing is their ability to capture the underlying dynamics of a time series
Okay.
in a way that's not only super informative, but also really elegant mathematically speaking.
So they go beyond just looking at the raw data points,
Exactly.
and they give you a more holistic view of how the time series actually evolves over time.
It's like the difference between looking at individual frames of a movie and actually watching the whole movie play out.
Okay, so it's less about the individual data points and more about understanding the journey.
Yes.
The overall flow of the data over time.
Precisely.
Okay, that makes a lot of sense.
Yeah.
And you mentioned mathematical elegance.
Yes.
What makes signature kernels so elegant from that mathematical perspective?
Well, they're deeply rooted in this really cool area of math called rough path theory.
Rough path theory.
Yeah, which deals with the analysis of these irregular paths you find all over in math.
Interesting.
So this connection to rough path theory gives signature kernels a really solid theoretical foundation
Okay.
and lets us use all these awesome mathematical tools that have been developed over the years.
So they're not just some random technique someone came up with.
Yeah.
They're built on this rich mathematical framework.
Exactly.
That's really cool. Now, you mentioned that signature kernels are particularly good at handling irregular data,
Yes,
which is something you see all the time in the real world.
all the time.
Can you talk a bit more about that?
Of course. So in many real-world applications, the data we collect isn't perfectly evenly spaced. Sometimes you have missing data points, or the sampling rate might change over time.
Mm-hmm.
And traditional time series methods often struggle with this kind of irregularity.
Yeah, they get thrown off.
But signature kernels are inherently robust to these issues.
So they can handle the messiness of real-world data.
That's a great way to put it. They're like the all-terrain vehicles of the time series world.
Uh-huh. I love that analogy.
They can handle those bumpy, unpredictable roads without breaking down.
And this robustness is a big deal,
A
right?
huge advantage because it means we can apply signature kernels to a much wider range of data sets without having to worry too much about data preprocessing or imputation.
That's a real time saver.
Absolutely.
This is all starting to paint a very impressive picture of what signature kernels can do.
They're pretty awesome.
But we keep coming back to this challenge of long time series and the computational bottleneck they create.
Yeah, that's the big hurdle.
Can you remind us why traditional methods struggle with these long sequences and how that memory issue actually pops up?
Sure. So with traditional methods, the memory they need to compute signature kernels typically scales quadratically with the length of the time series.
Quadratically meaning?
Meaning if you double the length of the time series, the memory requirements go up by a factor of 4.
Wow, that escalates quickly.
It does. And if you're dealing with time series that have hundreds of thousands or even millions of data points,
Oh, yeah?
the memory requirements can become absolutely enormous.
Like trying to fit the Library of Congress into a shoebox.
Exactly. It's just not going to happen.
So no wonder researchers have been trying to find ways to get around this limitation.
Absolutely. It's a major roadblock.
Okay, so with that context in mind, let's dive back into PowerSig and how it manages to sidestep this memory trap.
All right, let's do it.
You mentioned local Neumann series expansions earlier.
Yes.
Can you unpack that a bit more for us?
Sure thing. So let's start by thinking about the Gorsat PDE that characterizes the signature kernel.
Okay.
This PDE essentially describes how the signature kernel evolves over time.
All right, I'm following so far.
Now, the key insight is that this PDE can actually be rewritten as an equivalent integral equation.
So we're shifting from a differential equation to an integral equation.
Precisely. And while it might seem like a small change, it has huge implications.
How so?
Because this new perspective opens the door to using Neumann series expansions.
Okay. I'm intrigued.
Yeah.
But how do these Neumann series expansions actually help us with the memory problem?
Well, a Neumann series is a way to represent the solution to an integral equation as an infinite series of increasingly accurate approximations.
So like a series of better and better guesses.
Exactly. And each term in the series involves an integral. And the beauty of it is that we can just stop the series after a certain number of terms.
We don't need to go on forever.
Nope. And we'll still get a pretty darn good approximation of the solution.
So instead of trying to compute the exact solution to this integral equation.
Yeah, which can be a real pain computationally.
For sure.
We're strategically choosing a point and saying, okay, this is good enough.
We're drawing a line in the sand.
You got it. And this is where the dynamic truncation I mentioned earlier comes in.
Okay.
PowerSig has this really clever mechanism for determining how many terms to keep in the Neumann series for each of those little tiles.
Right, the tiles.
So it's making sure we strike that perfect balance.
A balance between
Accuracy and computational efficiency.
we want to be accurate, but we don't want our computers to melt down.
Exactly.
So just to recap, PowerSig breaks the problem down into smaller tiles, uses these Neumann series expansions to approximate the solution on each tile, and then dynamically truncates those series to keep things manageable.
You nailed it.
And by doing all this, they managed to significantly reduce the memory footprint while keeping the overall accuracy of the signature kernel.
It's like magic, but with math.
It's like they've compressed the information without losing any of the essential details.
A beautiful compression algorithm.
I'm really starting to grasp the genius of their approach.
It's pretty impressive stuff.
I'm excited to delve deeper into the nitty-gritty math of PowerSig, especially this dynamic truncation mechanism.
Me too. Let's get into the details.
Let's do it.
Okay, so we've kind of laid out the general idea of how PowerSig tackles that memory challenge, right?
Yeah, breaking down the problem using those localized Neumann series expansions.
Right, but now let's get into the actual nitty-gritty math of how it computes those expansions.
All right, let's do it.
It all starts with this clever little trick using something called the Chen-Flies series.
Chen-Flies series. Okay, that's a new one for me.
Yeah, it's a pretty powerful tool in rough path theory.
Right, rough paths.
Yeah, so basically it lets us express the solution of a controlled differential equation as this infinite series that involves iterated integrals of the control path.
So in this case, the control path would be the time series we're analyzing.
Exactly. And the signature kernel can be thought of as a special kind of solution to a controlled differential equation.
So the Chen-Flies series gives us a way to represent the signature kernel in terms of these iterated integrals.
Right, which essentially capture the cumulative effect of the time series' path.
It's like all the little steps the time series takes along the way.
That's a good way to think about it.
And the cool thing about the Chen-Flies series is that it's really well suited for recursive computations.
That's right.
And PowerSig takes full advantage of that recursive structure.
Exactly, to efficiently compute those local Neumann series expansions on each tile.
Okay, I see the connection. Now we're using the Chen-Flies series to express the signature kernel in a way that makes those recursive computations much easier.
But the question is, how do we actually perform those computations on each tile?
Right, that's what I'm wondering.
And that's where the power series come into play.
Okay, how so?
Well, the key insight is that the terms in that Chen-Flies series can actually be expressed as power series themselves.
Oh, interesting. So it's like series within a series.
Kind of, yeah. You can think of these power series as Taylor series expansions of the iterated integral.
Taylor series, I remember those from calculus.
Yep. They're basically approximations of a function using an infinite sum of powers of x.
And we're doing that around a specific point within each tile, right?
Exactly.
But wouldn't that mean we have to compute a separate Taylor series for every single term in the Chen-Flies series?
That's what you might think.
It seems like that could get really computationally expensive.
It would be, but luckily PowerSig has a trick up its sleeve.
Oh, good.
It uses this special relationship between the coefficients of the power series expansions.
Wait, so there's a connection between the coefficients?
Oh yeah, they're not independent of each other.
That's cool.
There's a really elegant mathematical structure there, and PowerSig exploits it to its advantage.
I love when that happens.
Me too. It turns out the coefficients for a given term in the Chen-Flies series can be computed recursively using the coefficients from the previous term.
So we don't have to start from scratch every time?
Nope, we only need to explicitly calculate the power series expansion for that first term. And then we can generate the expansions for all the following terms using that recursive relationship.
That's so clever. It's like a chain reaction.
It is. Each step builds on the one before it.
And that has to be what allows PowerSig to be so efficient.
Absolutely. It streamlines the whole computation of those local Neumann series expansions.
Making it much faster and easier to handle those really long time series.
Exactly. We're talking orders of magnitude faster.
That's incredible. Okay, so we've got the Chen-Flies series giving us a way to represent the signature kernel.
Yeah.
And then we're approximating those terms in the series using power series expansion. And we can compute those expansions efficiently using this recursive relationship between the coefficients.
It's a beautiful system.
It really is. But I have one more question about these power series expansions.
Okay, what is it?
You mentioned that they're centered around a specific point within each tile.
Right.
How do we choose that center point, and does it affect the accuracy of the approximation?
That's a great question, and you're right. The choice of center point definitely influences the accuracy.
So there's a trade-off. We want to pick a center point that's representative of the data in the tile.
Yeah.
But we also want to make sure the approximation stays accurate throughout the whole tile.
It's a balancing act, for sure.
So how does PowerSig handle that?
Well, they cleverly choose the center point to be the midpoint of each tile.
The midpoint, so right smack dab in the middle.
Exactly. It's like the Goldilocks point, not too far to the left, not too far to the right.
Just right.
Yep. It ensures that the power series expansion is fairly accurate throughout the whole tile.
While also being easy to compute.
Exactly. It's a win-win.
Okay, that makes sense. The midpoint seems like a natural choice.
Yeah.
But now I'm curious about how PowerSig actually calculates those power series coefficients.
Ah, good question.
Are there any special techniques or algorithms involved?
PowerSig uses a really neat algorithm based on Vandermonde matrices to efficiently extract those coefficients.
Vandermonde matrices now, those bring back memories of linear algebra class.
Yeah.
Good times, right?
Some good, some not so good.
Well, Vandermonde matrices are pretty special. They're matrices where each row is made up of consecutive powers of a number.
Okay.
And they have some really cool properties that make them useful in all sorts of areas of math, like polynomial interpolation and signal processing.
Interesting.
And in our case, PowerSig uses them to represent the relationship between those power series coefficients and the values of the signature kernel at certain points within the tile.
So the Vandermonde matrix is like a bridge between the power series representation and the actual values of the signature kernel.
That's a great analogy. It connects those two worlds.
I'm starting to see how this all fits together, but I have to ask, doesn't solving a Vandermonde system involve matrix inversions?
It does.
And those can be computationally expensive, especially for big matrices. How does PowerSig deal with that?
You're right. Matrix inversions can be a real pain, but PowerSig takes advantage of the special structure of Vandermonde matrices to make things easier.
Oh, so there's a shortcut. Kind of the inverse of a Vandermonde matrix has a very specific form that can be computed efficiently using a recursive algorithm.
So they found a way to avoid that computational bottleneck of matrix inversions.
Exactly. They're always looking for ways to optimize the process.
This is all incredibly impressive. Every step of PowerSig's algorithm seems to be designed for maximum efficiency.
That was the goal.
It's a beautiful example of how mathematical ingenuity can lead to real practical breakthroughs in computation.
I couldn't agree more. It's the perfect marriage of theory and practice.
Okay, so we've gone from the Chen-Fly series to Vandermonde matrices.
Quite a journey.
We've seen how PowerSig meticulously builds those local Neumann series expansions piece by piece, using all these amazing mathematical tools.
It's like a finely crafted Swiss watch.
But I'm curious, how do we actually stitch those local expansions back together to get a global representation of the signature kernel?
That's the next step, and it's where things get even more interesting.
Okay, so we've really dug into the math behind PowerSig, and it's clear that they've put a ton of effort into making it accurate and efficient.
Yeah, they didn't cut any corners.
But at the end of the day, the real test for any new method is how well it actually works with real-world data.
Right, you got to see it in action.
So what have the developers shown in their experiments?
Well, they focused on a pretty classic problem in time series analysis.
Okay.
Computing the signature kernel for two-dimensional Brownian motion.
Brownian motion, that sounds familiar.
Yeah, it's that random movement you see in like particles suspended in a fluid.
Right, like dust motes dancing in a sunbeam.
Exactly. It's a great benchmark because we understand it well theoretically. But it's a real challenge computationally, especially when you're dealing with longer paths.
So it's the perfect proving ground for PowerSig to show off what it can do.
Exactly, a trial by fire.
So what did they find?
The results were really impressive.
Oh, yeah.
First of all, PowerSig consistently hit high accuracy marks.
Okay, that's good.
And they did it with a surprisingly low truncation order for those power series expansions.
So they weren't using a ton of terms.
Nope. And that tells us that PowerSig is really good at grabbing that essential information in the signature kernel.
Without needing to go overboard with the computations?
Exactly. It's all about efficiency.
That's really encouraging.
Yeah.
It means we're not sacrificing accuracy just to make things run faster.
Right. It's the best of both worlds.
But let's talk about the big one, memory usage.
The elephant in the room.
That's been the main roadblock for all the traditional methods.
Absolutely a real pain point.
How did PowerSig handle it?
This is where PowerSig really shines. The experiments showed that its memory consumption is way lower than existing methods.
Like how much lower?
We're talking orders of magnitude lower.
Wow, that's huge.
They were able to handle time series with hundreds of thousands of data points.
Yeah.
Using just a tiny fraction of the memory that other approaches need.
That's a game changer.
Yeah.
It means we can finally analyze data sets that were just completely out of reach before.
It's opening up a whole new world of possibilities.
It's like they shrunk down a supercomputer into something that fits in your pocket.
Exactly, and it all comes down to that localized approach.
Right, breaking the problem into smaller pieces.
By carefully managing those local approximations, they've managed to escape that memory curse.
That's amazing. Okay, so PowerSig is accurate. It's memory efficient.
Check and check.
But what about runtime? How does it stack up in terms of speed?
Well, the experiments showed that PowerSig can be significantly faster, especially when you're dealing with those long time
So
series.
not only does it save memory, it saves time, too.
It's a win-win situation.
That's awesome. Okay, so it's accurate, it's efficient, it's scalable.
It ticks all the boxes.
Sounds like PowerSig is the real deal, a powerful new tool that could completely change how we analyze time series data.
It has the potential to be a real game changer.
It's incredible to see how these researchers have taken this deep theoretical understanding of signature kernels and turned it into this practical and powerful computational tool.
It's a testament to the power of human ingenuity.
It really is. PowerSig isn't just a technical achievement.
Right.
It's a story about the power of curiosity and the drive to push the limits of what's possible.
To explore the unknown.
It makes you wonder what other mathematical treasures are out there just waiting to be discovered
I think there are many more.
and transformed into tools that could change the world.
Absolutely. The potential is limitless.
Well, that brings us to the end of our deep dive into PowerSig.
I hope you enjoyed the ride.
We've explored the heart of a truly groundbreaking new method in time series analysis.
A real revolution in the making.
We've seen the power of mathematics, the elegance of those solutions, and the potential for these kinds of scientific breakthroughs to completely reshape our understanding of the world.
It's an exciting time to be alive.
Until next time, keep exploring, keep asking questions, and keep pushing those boundaries of knowledge.
Stay curious, my friends.
Okay, so anyone who's worked with complex time series data knows this feeling, right? How do you analyze those massive data sets without, like, your algorithms just completely choking, on the sheer volume of information?
Yeah, it's a challenge for sure, especially with data that's, really volatile, or if it's sampled at super high frequency.
Exactly. Like, imagine you're trying to analyze, like, a year's worth of sensor data from a self-driving car.
Mm.
Or, I don't know, modeling financial markets, but with like millisecond level precision.
Right.
It's crazy how fast the memory demands just explode.
Oh, absolutely. And that's kind of where signature kernels come in, right? They're a really powerful tool for this because they give us a way to capture the essence of a time series. So like its shape, its dynamics, without like getting bogged down in all the individual data points.
It's almost like having a mathematical fingerprint for each time series. Is that a good way to think about it?
Yeah, that's a great analogy. The signature of a time series, it's this really compact, elegant mathematical object, and it captures the key features of how it moves over time. It's kind of like a DNA sequence, but for the data's behavior.
Okay, that makes sense. So we have these powerful signature kernels that can help us compare and analyze these complex time series. But like you were saying, the traditional methods for computing them, they often just hit a wall, especially when we're talking about like really big data sets.
Yeah, that's right. Methods like dynamic programming or like global PDE solvers, they tend to treat the whole time series as one big chunk, which gets really expensive computationally as the data grows.
Right.
Yeah.
It's like trying to solve this giant jigsaw puzzle all at once.
Exactly. And that's what makes this paper we're looking at today so exciting. It's called Scalable Signature Kernel Computations for Long Time Series via Local Neumann Series Expansions. And it basically proposes a totally different way of thinking about this whole problem.
Okay, I'm definitely intrigued. So what's the key insight here?
So instead of trying to conquer the entire time series in one go, they break it down into smaller, more manageable chunks. They call these tiles.
Oh, okay. So it's kind of like solving that jigsaw puzzle one section at a time.
Exactly. And by working on these like localized tiles, they can really bring down the memory footprint of the whole computation.
Makes sense. But how do they actually compute the signature kernel on each of those tiles?
Okay, so this is where things get really clever. They use something called Neumann series expansions, which are essentially a way of approximating the signature kernel, but piece by piece using this recursive approach.
Neumann series. Okay, I vaguely remember those from my calculus days. Could you maybe give us a quick refresher?
Sure. So basically, a Neumann series lets you approximate a function as an infinite sum of terms. And in this case, they're using it to approximate the solution to a certain type of integral equation, which defines the signature kernel.
Okay, so they're breaking the problem down into these tiles, right? And then on each tile, they use these Neumann series to approximate the signature kernel piece by piece. But how do they ensure that, it all comes together correctly in the end.
That's where the recursion comes in. The way they've designed the algorithm, the solution on each tile actually depends on the solutions from its neighboring tiles. So it's kind of like this chain reaction almost, where information propagates from one tile to the next.
Oh, I see. So they start with a tile where they know the boundary conditions and then use that information to compute the solution on the next tile and
Yeah.
so on.
And because each tile's computation is relatively independent, the whole thing can be parallelized, which makes it even more efficient.
Okay, that's starting to make a lot of sense. But there's one part of the title that's still kind of bugging me. Dynamic truncation. What does that mean exactly?
Yeah. So that's one of the coolest things about this approach. The algorithm doesn't just blindly compute a fixed number of terms in the Neumann series. It actually adapts on the fly. It figures out how many terms are needed to achieve a certain level of accuracy for each tile.
So it's like a chef adjusting the seasoning based on taste. No wasted effort, just precise calculations tailored to each tile.
Precisely. And this dynamic truncation, it not only saves a ton of computation time, it also makes sure they're getting the most accurate results possible, within a given computational budget, of course.
This all sounds incredibly efficient. I'm definitely eager to see how it performs in practice. But before we jump into that, can we maybe take a step back just to make sure everyone's on the same page about what exactly we're trying to compute here? Can you walk us through, like, the definition of the signature kernel and the challenges it presents?
Absolutely. So let's start with the signature of a path. Imagine you have a continuous path, we'll call it x. It's in d-dimensional space, and it's parameterized by time, t. Mathematically, we'd write this as x0, t r sub.
Okay, so this could represent anything from, like, the trajectory of a particle to the price fluctuations of a stock over time.
Exactly. Now, the signature of this path, it's a sequence of iterated integrals of x. For each positive integer, k, the k8th level of the signature, we denote that as sx and that's actually a tensor of order k.
Okay, so we're talking about tensors here, not just simple vectors or matrices.
Right. And each entry in this tensor is given by the integral. Cax, if aabot dx, tiwax desinoid iot kid ok afp ok. xi1t1.dx
Wow, okay, so basically we're integrating over all possible increasing sequences of times within the interval from 0 to t. And for each of those sequences, we're multiplying the increments of the path along different dimensions.
Exactly. And the beauty of this signature is that it captures like all the path information, but in this hierarchical way. The lower levels capture the basic increments of the path, while the higher levels capture more complex interactions and patterns.
So it's not just about where the path ends up, it's about how it gets there. The twists, turns, the oscillations, it all contributes to the signature.
Precisely. Now, when we talk about signature kernels, we're essentially using this signature to define a measure of similarity between different paths.
So given two paths, like x and y, we can use their signatures to determine how similar their shapes and dynamics are.
Exactly. One common way to define a signature kernel is to take the inner product of the signatures of the two paths, but truncated at a certain level.
So if we truncate at level n, the kernel would be xyn dol sexy syn wrangle.
You got it. And the choice of truncation level n depends on the complexity of the paths and how much detail we want to capture.
Right, right. But as we've discussed, computing this inner product, especially for high truncation levels and large data sets, that can be computationally very expensive.
Absolutely. Traditional methods require calculating and storing all those iterated integrals, which can quickly become intractable.
And that's where this whole tile-based approach with Neumann series expansions really shines.
Exactly. By breaking down the problem into these smaller pieces and using these series expansions, we can dramatically reduce that computational burden.
Okay, yeah, I think I'm starting to get the full picture now. We have these signature kernels. They offer a really powerful way to analyze and compare complex time series data.
Right.
But their computational demands have always been a major bottleneck.
Right.
And this new approach with this clever combination of tiling, recursion, and Neumann series expansions, it really seems to offer a way to overcome those limitations and like finally unlock the full potential of signature kernels.
I think so, yeah.
Well, I'm definitely hooked. Let's dive into the details of how this algorithm actually works.
All right, so welcome back to our deep dive into these signature kernels. They're pretty fascinating, right?
Yeah, definitely. Last time we kind of set the stage. We talked about all the challenges of analyzing these complex time series. And we introduced the idea of signature kernels as this, this powerful tool for really capturing what's going on in these data streams.
Right. And we also hinted at this groundbreaking new approach For computing them efficiently, it's all based on breaking the problem down into smaller tiles and then using these local Neumann series expansions.
Yeah. It's like we were saying, it's like tackling a huge jigsaw puzzle, but one section at a time, instead of trying to put the whole thing together all at once.
Exactly. And today we're going to get into the, the real nitty-gritty, the mathematical core of this whole approach. Are you ready to dive into some lemmas and propositions?
Oh, absolutely. I'm really curious to see how these kind of abstract mathematical concepts actually translate into a practical algorithm. One that can handle these massive time series data sets we were talking about.
All right, great. So let's start by revisiting the definition of the signature kernel. As we discussed, one common approach is to use the inner product of the truncated signatures. So for two paths, x and y, truncated at level n, the kernel's given by, or OPM, SXN, SYN ring.
Right. And the challenge lies in efficiently computing this inner product, especially when we have high truncation levels and large data sets.
Exactly. Now, the key insight that this paper leverages is that this inner product can be expressed as the solution to a certain type of partial differential equation, a PDE. They call it a Gaursat problem.
Okay, so we're going from signatures and inner products to PDEs. How does that help us?
Well, PDEs, even though they can be really complex, they have a lot of rich mathematical theory behind them, which gives us all sorts of tools and techniques to find solutions. And in this case, the Gaursat problem that's associated with the signature kernel, it has a special structure, and that lets us rewrite it in a more manageable form as a Volterra-type integral equation.
Volterra equations. Okay, those ring a bell vaguely.
Okay.
I think those are the ones that involve integrals where the limits of integration depend on the variable of integration, right?
Exactly. And the reason that this Volterra form is so useful is because it lends itself really well to this recursive solution, especially when we combine it with the idea of tiling the domain.
Okay, I'm starting to see the connection here. So we break down the domain of the problem, which represents like the time interval of our paths, into these smaller tiles. Yeah. And then we use the Volterra equation to recursively compute the solution on each tile, using the information from the neighboring tiles.
Exactly. It's like we're solving a really complex equation by breaking it down into a series of smaller ones, interconnected equations, each of which is easier to solve.
Yeah, that's a really clever approach. But there's got to be more to it than just like tiling and using the Volterra equation, right? How do those Neumann series expansions fit into all of this?
So that's where things get really interesting. The key to efficiently computing the solution on each tile is actually using those Neumann series expansions. And these basically give us a way to approximate the solution as an infinite sum of terms.
Okay, so instead of trying to directly solve the Volterra equation on each tile, which could be really computationally expensive, we approximate it using these series.
Exactly. And the great thing about these Neumann series is that under the right conditions, they converge really quickly. So that means we don't need to compute all infinitely many terms to get a good approximation. We can just truncate the series after a certain number of terms. And we know that the remaining terms are going to have a really small impact on the overall accuracy.
So it's kind of like approximating pi to a certain number of decimal places. We don't need infinite precision to get something useful, right?
That's a perfect analogy. And the choice of how many terms to include in that truncation, it depends on how much accuracy we want and also the characteristics of the data itself.
So it's a trade-off.
That's a great question. And the answer is actually in a crucial mathematical result. It's presented in the paper as lemma 3.3. And it establishes this key property of the integral operator involved in the Volterra equation, specifically that its spectral radius is 0.
Spectral radius, huh? That sounds a little bit intimidating. Can you break that down for us?
Sure. So the spectral radius of an operator, it's essentially a measure of how much it stretches or shrinks vectors when we apply it repeatedly. And in this case, having a spectral radius of 0 for our integral operator, it means that when we apply it repeatedly, its effect diminishes really rapidly.
So it's kind of like hitting a tennis ball against a wall over and over again. With each bounce, the ball loses energy, and eventually it's just going to come to a stop.
Exactly. And that property is what guarantees that the Neumann series converges quickly. Remember, these series, they're basically just repeated applications of the integral operator. So as we add more terms, the impact of each additional term shrinks rapidly because of that 0 spectral radius.
Okay. I think I'm starting to see the connection now. So lemma 3.3, by showing that the spectral radius of the integral operator is 0, it basically provides the foundation for using these Neumann series to efficiently approximate the solution on each tile.
Exactly. It's the mathematical bedrock that this whole approach relies on.
But wait a second. Why is proving that the spectral radius is 0 so important for the Neumann series convergence? It seems like a detail we could just kind of gloss over.
Oh, no, not at all. It's really the heart of the matter. Without that property, we wouldn't have any guarantee that our series would converge, let alone converge quickly. It'd be like building a house on sand instead of solid ground.
Oh, I see, I see. It's not just some mathematical curiosity. It's what makes this whole approach actually feasible. Okay, that makes even more sense now. But how do we actually go about proving this lemma?
So the proof involves showing that for any complex number that isn't 0, the operator that we get by subtracting the integral operator from a scaled identity operator is bijective. In simpler terms, it means this modified operator has a unique solution for any input we give it.
Bijective. Okay, so that means for every output, there's a unique input, and vice versa.
Exactly. And to prove this bijectivity, they use something called the Picard iteration. It's this iterative method for constructing a sequence of functions that converge to the solution of an integral equation.
So it's kind of like we start with an initial guess for the solution, and then we keep refining it using the integral equation until we get like arbitrarily close to the true solution.
Precisely. And the key here is that these Picard iterators form what's called a Cauchy sequence, meaning that the difference between successive iterates gets smaller and smaller as we go further down the sequence.
So the iterates are getting closer and closer together, basically zeroing in on the actual solution.
Exactly. And because the space where these iterates live, what we call the function space, is complete, meaning every Cauchy sequence converges to a limit within that space, we know that these Picard iterates have to converge to a unique solution.
Okay, I'm following the logic here.
Mhm.
So by showing that the Picard iterates converge to a unique solution, we prove that our modified operator is bijective. And that, in turn, implies that the spectral radius of our original integral operator must be 0.
Exactly. You've got it. It's a really elegant example of how these, seemingly abstract mathematical concepts can be used to figure out concrete properties, and then those properties underpin these powerful algorithms.
Wow, this is really insightful. We've gone from the basic definition of a signature kernel all the way to the intricacies of this Gaursat problem, the Volterra equation, and this crucial lemma 3.3, which basically establishes that using Neumann series is even feasible in the first place. It's kind of like peeling back the layers of a mathematical onion. Each level reveals even more intricate structures.
I couldn't have said it better myself. It's this really cool back and forth between theoretical insights and algorithmic ingenuity that makes this paper so compelling.
I am completely hooked. I can't wait to see how these Neumann series are actually computed and how that whole dynamic truncation scheme works in practice.
All right, welcome back. We're right in the middle of unpacking this incredibly clever approach to computing signature kernels. And this method, it's really promising, right? It could make analyzing complex time series data way more efficient. We've laid down the mathematical groundwork, but I'm ready to see how all this comes together in a real practical algorithm.
Okay, yeah, that's exactly where we're headed. So remember, we talked about breaking the problem down into these tiles and then using these Neumann series to approximate the solution on each tile.
Right.
But the real cleverness, the real beauty of this whole thing lies in how those series are actually computed.
Okay, yeah, let's get into the details then. How do they actually go about calculating those Neumann series coefficients, especially when we're dealing with data sets that could be absolutely massive? So this is where proposition 3.5 comes in. It gives us this recursive formula for computing the signature kernel on each tile. And it takes advantage of the fact that the solution on a given tile, it actually depends on the solutions on its neighboring tiles.
Ah, okay. So we're sort of building up the solution tile by tile, using information from the tiles below and to the left, right?
Exactly. Proposition 3.5 tells us that the solution on a tile, it can be expressed as this infinite sum of terms. And each term involves the integral operator applied to the boundary values of the kernel on those neighboring tiles.
Right, right. Okay, so we have this recursive formula, but it involves these infinite sums. We can't actually compute infinitely many terms in practice, can we?
That's right. That's where truncation comes into play. We don't have to calculate all infinitely many terms in those Neumann series. We can just truncate them after a certain number of terms, because we know that the terms we leave out, they'll have a really negligible effect on the overall solution.
So it's all about finding that balance
Yeah.
between being accurate and being computationally efficient.
Exactly. And what's really cool is that this algorithm, the one proposed in this paper, it actually uses this dynamic truncation scheme. So it adapts the number of terms it uses on the fly based on how accurate we need the result to be and also on the characteristics of the data itself.
Ah, that's so smart. So it's like a chef, right, who just instinctively knows how much seasoning to add without like overpowering the dish.
Exactly. That's a great analogy. This dynamic truncation, it not only saves a bunch of computation time, but it also makes sure that we're getting the most accurate results we can, given the computational budget we have, of course.
That's really impressive. But I'm still kind of curious about how those Neumann series coefficients are actually calculated. I mean, we could be working with huge data sets here, right? So efficiency is key.
Oh, absolutely. And that's where Proposition 3.8 steps in. It gives us this powerful tool for computing those coefficients, the ones in the Neumann series expansions. And the key insight here is that these coefficients, they can be represented using matrices. And we can compute those matrices recursively using this clever Vandermonde scheme.
Vandermonde scheme. Okay, that rings a bell. I think it's from linear algebra, right? Can you remind me how it fits into all of this?
Sure. So remember, those Neumann series, they involve powers of S and T. Those represent the coordinates within each tile. And the Vandermonde scheme, it basically gives us this elegant way to represent the relationship between those powers and the corresponding coefficients, all using matrices.
Ah, I see. So we're basically using matrices to keep track of all those coefficients
Yeah.
and their dependencies across the different tiles.
Precisely. And by carefully choosing the center point for the power series expansion on each tile, we can actually simplify those matrix operations significantly, which makes the whole computation even more efficient. It's all about finding the most streamlined way to organize and manipulate all those coefficients.
So it's like optimizing the assembly process for our jigsaw puzzle, right? We want to minimize the number of moves and connections we need to make.
Exactly. And this attention to detail, this focus on optimizing those matrix operations, is what allows this algorithm to scale to those massive time series data sets, the ones that we couldn't even dream of handling before.
Okay, wow. So we've got this really intricate system here, right? Tiling, recursion, Neumann series expansions, the Vandermonde scheme, it's all working together to compute these signature kernels efficiently. I gotta say, it's a pretty elegant solution.
I think so too. It's a really beautiful example of how we can take these abstract mathematical concepts and use them to create practical algorithms that can have a real impact.
Well, speaking of real impact, I'm really curious to know how this algorithm actually performs, in the real world. Does it really live up to all the hype? Is it really as efficient, scalable, and accurate as they claim?
That's the ultimate test, right? And to answer that, we need to look at the experimental results from the paper. They did a whole bunch of benchmarks comparing their algorithm, which they call PowerSig, to other state-of-the-art methods for computing signature kernels.
Oh, cool. So it's PowerSig going up against the reigning champs. What happened?
Well, let's just say that PowerSig really put on a show. They focused on computing the self-signature kernel of two-dimensional Brownian motion. It's a classic problem in stochastic analysis.
Brownian motion. Okay. That's the random movement of particles suspended in fluid, right?
Exactly. And it's used to model all sorts of things, from stock prices to the movement of molecules. So what they did was they generated these Brownian motion paths. And they kept increasing the length of the paths to really push those existing algorithms to their limits.
Ah, so they were really trying to stress test this new approach, see if it could handle the pressure.
Exactly. And the results were really impressive. PowerSig consistently outperformed those other methods, both in terms of how much memory it used and how long it took to run, especially as they made those time series longer and longer.
Okay, give me some numbers. How much more efficient are we talking about here?
All right, get ready for this. PowerSig was able to compute the signature kernel for time series with up to 500,000 points, and it used less than 100 megabytes of GPU memory. To give you some context, the other methods, they were already hitting their limit at just a few thousand points, and they needed way more memory, like orders of magnitude more.
Wow, that's incredible. It's like comparing, like sleek sports car to a giant lumbering truck. PowerSig is on a whole other level when it comes to efficiency.
I'd say so, yeah. And this memory efficiency, it translated directly into faster runtimes. PowerSig was crunching through those 500,000 point time series in seconds, while the other methods, they would have taken hours, maybe even days, to do the same thing.
So it's not just about being able to handle those bigger data sets. It's also about getting the results faster, which is, really important for things like real-time analysis. and decision-making.
Absolutely. This level of speed and efficiency, it opens up so many new possibilities. Now we can finally tackle problems that we thought were impossible before.
Mm.
We can analyze data in real time, and we can potentially discover insights that we could never have imagined before.
This is really groundbreaking stuff. It seems like any field that works with large-scale time series data could really benefit from this.
I think you're absolutely right. This paper, it represents a fundamental shift in how we think about working with complex time series data. And its impact, I think it's going to be felt in so many different areas.
I'm totally convinced. This has been an incredible deep dive. We have explored the math behind this new algorithm. From that Gorsat problem to the clever use of Neumann series expansions and the Vandermonde scheme. But beyond all those technical details, what really stands out to me is the potential. The potential this approach has to uncover new discoveries and new insights in so many different fields.
I totally agree. It's a testament to the power of mathematical innovation, to push the boundaries of what we think is possible and to create tools that help us understand the world around us in new ways.
That's what the deep dive is all about. Thanks for joining us on this journey. And to our listeners, keep exploring, keep questioning, and keep pushing those boundaries of knowledge. We'll see you on the next deep dive.